Hello, and welcome to our lecture on inequalities. We've been using inequalities already in these lectures. For example, the domain of the square root function was all x greater than or equal to 0. That's an inequality, and it can be written in a different notation as the interval 0, infinity. That sideways 8 is the infinity symbol, and I'll talk about that symbol in a moment. But notice the 0 has a bracket to its left. That's because 0 is included in the set. Okay, now before we talk about inequalities in greater detail, let me remind you that we aren't going to use complex numbers in this lecture. That said, I'll make a comment about complex numbers and inequalities a little bit later, but we're dealing now with real numbers, inequalities involving real numbers. Let me remind you of some of the notation that we use in inequalities. For instance, the notation a comma b with brackets around the a and the b, that's the closed interval ab. It's all real numbers between a and b and including a and b. And you can write it as a less than or equal to x less than or equal to b. In a similar notation, a comma b with parentheses means the open interval. The endpoints are not included. It's a less than x less than b. All numbers between a and b, but not including the endpoints. Another notation is a comma infinity, and that means all values of x greater than or equal to a. And if you want to go the other direction, the notation minus infinity comma b would mean all x values less than b. So I hope this notation's familiar to you. Let's apply it to a simple example. What's the domain of the function square root of x plus 4? The square root of the quantity x plus 4. Well, we know about square root functions. They have to be greater than or equal to 0. So we have x plus 4 greater than or equal to 0, or x greater than or equal to minus 4. And hence, using this notation, we could write the domain as the interval minus 4 comma infinity, putting a bracket next to the minus 4. Here's a picture of the square root of x plus 4. It's looks like the square root function, doesn't it? But it's been shifted 4 units to the left. And down below this picture, I've drawn the x-axis with the domain indicated by a sort of a red line starting at minus 4 and going off to the right. And this indicates that the domain starts at minus 4 and grows without bound. Okay, I've been using this infinity symbol, and you see it all the time in mathematics. Let's be very careful here. Infinity is not a number. It's a concept. It means you go on forever. And so don't write intervals with infinity symbols and brackets. Make them open parentheses. It's incorrect to write in mathematics the expression minus 4 comma infinity using brackets around both sides. The correct way to write it is infinity with a parentheses around it. Again, infinity is a concept. It's not a real number. Okay, you've probably seen properties of inequalities when you've studied mathematics. Let me review some of the simpler ones, and then we'll do some harder ones. A less than B and B less than C implies, of course, that A is less than C. For instance, if 2 is less than 5 and 5 is less than 7, then 2 is less than 7. That's called transitivity. Another very common property is if A is less than B and C is less than D, and I add them up, then A plus C, of course, will be less than B plus D. And another property, if A is less than B and I add the same quantity to both sides, A plus C would be less than B plus C. Those are pretty obvious properties of inequalities. Let's turn now to a difficult property, one you have to be careful of. If you have A less than B and you multiply both sides by a constant, you have to be a little careful here. If the constant's positive, no problem. Then AC will continue to be less than BC. But if that constant is negative, you've got to flip the inequality. AC will be greater than BC. Let me show you a quick example of this. Do we all agree that 2 is less than 5, right? Well, let's multiply both sides by minus 3. What'll I get? Well, the left side will be 2 times minus 3, the right side will be 5 times minus 3, and I claim the inequality has to reverse. So now it's minus 6 greater than minus 15. So I started with 2 less than 5, I multiplied by a negative number, and my output is an inequality in the opposite direction. And of course, minus 6 is greater than minus 15. Minus 15 is more negative than minus 6. All right, let's do some equations involving inequalities. These kinds of equations occur all the time in pre-calculus and calculus classes. Here's a fairly easy one. Suppose you want to solve for x in the equation 1 minus 3 halves x greater than or equal to x minus 4. So this is an inequality that we want to solve for x. Okay, how could we do it? Well, there are many ways of attacking this. I'll show you one way. You might have a different way to do it. The first thing you might do is multiply both sides by 2 to get rid of that fraction. So you have 2 minus 3x greater than or equal to 2x minus 8. Note that 2 is positive, so I don't have to worry about reversing the inequality. Then I could do the following. I could take the 2x and bring it to the other side. In other words, add minus 2x to both sides, and I have 2 minus 5x greater than or equal to minus 8. Okay, we're almost there. Minus 5x now is greater than or equal to minus 10 by bringing the 2 to the other side. And I want to get x all by itself, all lonesome. Well, I have to divide by minus 5, don't I? Well, when I do that, I reverse the inequality. So x is now less than or equal to minus 10 divided by minus 5, which of course is equal to 2. So the final answer is x less than or equal to 2. And I invite you to check some values here. If you look at certain x values, you'll see that if you plug in x less than or equal to 2, the original inequality is satisfied. And if you plug in values greater than 2, you'll discover that the inequality is not satisfied. For instance, if I plug in 0, 0 is less than or equal to 2. If you plug in 0, the inequality, the original inequality, would be 1 greater than or equal to minus 4, which is a true statement. Okay, let me reiterate that pitfall about multiplying or dividing by negative numbers. If you do that, you have to reverse the inequality. Another example, because this is really, this comes up all the time, this kind of mistake of not reversing the inequality. Minus 3x is less than 12. Suppose that's an inequality you want to solve. Well, what would you do? You would divide by minus 3 and reverse the inequality. So that would be x greater than 12 divided by minus 3, or x greater than minus 4. Now, that said, you can avoid this reversal of the inequality by solving this slightly differently. You could start with minus 3x less than 12 and move the 12 to one side and the minus 3x to the other side, and you have minus 12 less than 3x. Now divide by 3. 3 is positive, and you get minus 4 less than x, which is equivalent to x greater than minus 4. I got the same answer. All right, let's go something a little bit more difficult now. Inequalities involving absolute values. Trust me, this kind of expression occurs all the time in calculus courses, and they're kind of difficult to deal with, I find. Let me show you some of the rules here. Assume a is a positive number, and if you see the expression absolute value of x less than a, then that's equivalent to minus a less than x less than a. In a sense, x is in a sandwich. It's stuck between minus a and a. For instance, if the absolute value of x is, say, less than 3, that means that x is in between minus 3 and 3. For example, x could be 0 or 1 or 2 or minus 1 or minus 2, but x can't be 5 or minus 10. So that's one property, absolute value of x less than a. Then there's a similar property where you have absolute value of x bigger than a. And this is a little more complicated. The solution to that is x less than minus a or x bigger than a. Let me show you an example of this. Absolute value of x bigger than 5. The solution to that inequality would be x less than minus 5 or x bigger than 5. For instance, minus 20 is okay, and so is 50. But 2 is not okay. The absolute value of 2 is not bigger than 5. So that's kind of complicated because it's got two pieces. This answer is some numbers here or some numbers over here. All right, let's do an example of these ideas. Suppose we have absolute value of x minus 5, the quantity x minus 5, less than or equal to 2. Let's solve that inequality. Well, the rule is when you have less than or equal, it means that the x minus 5, the thing inside the absolute value signs, is caught in the sandwich. And the sandwich is between minus 2 and 2. So we write x minus 5 less than or equal to 2 and greater than or equal to minus 2. And then add 5 to all three sides, and you have 3 less than or equal to x less than or equal to 7. The solution is the closed interval 3, 7. Let me show you a picture of that closed interval. There I've drawn it, and it's got brackets at 3 and at 7, and all the numbers in between are the solutions to that inequality. Okay, good. Let's reverse it. Let's solve the inequality now with greater than 2 instead of less than 2. This is a little more complicated. So what's it mean to say the absolute value of x minus 5 is greater than 2? Well, the rule is that means that the thing inside the parentheses, x minus 5, is either less than minus 2 or bigger than 2. So I have two inequalities. I have x less than 3 when I add 5 to both sides, or I have x greater than 7. And that's a good way to write the answer. All the numbers less than 3 are okay, and all the numbers greater than 7 are okay, but nothing in between. Now, how do you write this in interval notation? Let me show you how mathematicians would write this. They would say, well, that first interval is minus infinity to 3, and it's an open interval at 3. Union, and I'll talk about that union symbol. That means or. So it includes also the numbers that start at 7, not including 7, and go off to plus infinity. So it's the union of two sets. Here's a picture of the number line with the solutions to that second problem. It's all the numbers to the left of 3 together with all the numbers to the right of 7. All right, good going. That's a hard type of skill, and I used a notation there that you might not be very familiar with. It's set notation. Let me remind you or talk about set notation for a minute. In set theory, you talk about unions of sets and intersections of set. The union symbol is like a U, and A union B, the union of two sets, means all the numbers that are in A together with all the numbers are in B. So it could be a giant set. The intersection of two sets, A intersection B, and now the symbol is an upside down U, that means all the numbers that are in both A and B simultaneously. It's the overlap of the two sets. And that could be much, much smaller than the union. So you'll see that notation when you read mathematics textbooks, etc. Let me show you a pitfall. I've seen this expression many times as a teacher. I'll see students write this and see if you can figure out what's wrong with it. It kind of looks okay initially, and then you sort of say, wait a minute, something's wrong with this. Remember that last example we did? The answer was x less than 3 or x bigger than 7. And some people want to write that as the following: 7 less than x less than 3. Sort of compactify that notation into one little expression like that. Well, what's wrong with writing that? It's kind of bizarre, but that's incorrect mathematics. There are no numbers, x, that simultaneously are bigger than 7 and at the same time they're less than 3. You can't describe that solution set from that previous problem in one single expression. You have to split it into two pieces. X less than 3 union x bigger than 7. So be careful when you write an expression like that. You can see why it's wrong, I think. 7 is not less than 3, is it? So it can't be right. Okay, let's do an example from calculus. I got this problem out of a calculus textbook, but it involves pre-calculus skills. Much of calculus deals with pre-calculus skills. And here's the problem. I won't tell you where it came about, what the calculus problem was, but it boiled down to the following skill. Can you find the open intervals where this function is positive? And the function is 2x squared plus 5x minus 12. So it's some parabola. Where is the parabola positive? Well, here's one way to attack it. Take that parabola and factor it. And it turns out to factor nicely as x plus 4 times 2x minus 3. And I want that expression, the product of those two factors, to be greater than 0. That's my goal. Well, let's think about this. When is that expression equal to 0? Well, it's equal to 0 at minus 4 and at 3/2. Minus 4 makes the first term 0, and 3/2 makes the second term 0. Those are kind of the key points here. And to either side of minus 4 and either side of 3/2, the term will either be positive or negative. So I like to form a chart showing the positive and negative values of this product of the two factors. Let me show you what I mean by this. Let's take the numbers greater than 3/2. If you're a number greater than 3/2, then x plus 4 is positive. And so is 2x minus 3, so the product of two positives is positive. So to the right of 3/2, I put little plus signs, because I know the product is positive there. Now let's look to the left of minus 4. If x is less than minus 4, and you can imagine x being, say, minus 10, then the first factor, x plus 4, is negative, and the second factor is also negative. Negative times negative, positive, so I put little plus signs above the line starting at minus 4 and going off to minus infinity. What about in between minus 4 and 3/2? Well, I think you see what's going to happen. If you plug in a number in between those two key points, how about if I plug in 0? The product, x plus 4, is positive. The second term, 2x minus 3, is negative. Positive times negative, negative. So I put little negative signs between minus 4 and 3/2. Okay, I've analyzed now the factored form of this quadratic along the number line using those two key points, minus 4 and 3/2. And what have I discovered? I've discovered that to the right of 3/2 and to the left of minus 4, the expression is positive. So that's the solution. The solution is, in interval notation, minus infinity to minus 4, open interval, union 3/2 to infinity. By the way, here's a picture of that polynomial. It's slightly below the x-axis, and you can see that it's positive on the left of minus 4 and on the right of 3/2. Kind of interesting how we could solve that without looking at the picture and using our ideas of intervals. Now, some examples of inequalities have strange solution sets. I mean, they aren't that strange, but they're kind of surprising solution sets. Let me show you a couple of simple examples where the answer is like, oh, that's kind of weird. For example, let's solve the inequality x squared plus 2x plus 4 greater than 0. Okay, let's solve for x. What x values render this polynomial positive? Well, many ways to approach it. One way might be to complete the square. Remember we did that skill a few lectures ago. What would I need to add to x squared plus 2x to make it a perfect square? Well, I have to add 1. And then I'll take 1 out of the 4, and that leaves 3. And so x squared plus 2x plus 1 can be factored as x plus 1 squared plus 3. And I want that to be positive. Well, what do you think? Take a look at it. For what values of x is that positive? Well, gosh, for any value of x you put in, that x plus 1 squared is greater than or equal to 0, and you're adding 3 to it, so it's always positive. So the solution set is all real numbers. Every real number satisfies that inequality. And you would write that in notation, the interval minus infinity, comma, infinity, with parentheses on both sides. That's a great solution set. Everybody is in the solution set. Here's a graph of that polynomial, and notice that it's above the x-axis. And in fact, the vertex down there, minus 1, 3, was indicated when we completed the square. We noticed that when x was minus 1, the polynomial was equal to 3 there, and then the polynomial is above its vertex, and hence, for all x values, f of x is positive. Let's do the same example, but reverse the inequality. X squared plus 2x plus 4 less than 0. Well, now I think you see what happens. There are no x values that work here, right? For no value of x will this be less than 0. How do you express that mathematically? Well, the solution set is the so-called empty set, or the null set. And it's often written as a 0 with a slanted line through it, or it's sometimes in set notation, you'll write the brackets, the parentheses, and it's just empty inside. There's nothing inside the set. Okay. Let's do one more. Again, very similar to what we just did. Let's do x squared plus 2x plus 1 less than or equal to 0. What values of x satisfy that inequality? Well, how am I going to approach that? How about if I factor it? X plus 1 squared less than or equal to 0. Well, now wait a minute. X plus 1 squared is always greater than or equal to 0. And in fact, it's 0 when x is minus 1. So that's the only value of x that works. This solution set consists of a single number, all alone. It's not an interval anymore, is it? It's just a single number, the number minus 1. Okay, good. I hope we're sort of comfortable playing with solving these inequalities, finding the solution sets to inequalities. I don't think it's an easy skill, by the way. And oftentimes students ask me the following question: Professor, why are we doing this with real numbers? Couldn't we do inequalities with those complex numbers? You might remember we studied complex numbers a few lectures ago. They are the form a plus bi, where I was the square root of minus 1. Well, it turns out you can't order the complex numbers and use these inequality properties with the complex numbers. It just doesn't make any sense. It's kind of interesting that it makes no sense to say that one complex number is greater than another complex number. Now, you can sort of say it. You could say something like this. Remember how we graphed complex numbers in the plane? You could say that this complex number is closer to the origin than this one over here. You could say that. But that's not very good, because if you had a circle in the complex plane, then they would all be the same distance to the origin. And so how would you order them? So it's a curious fact of mathematics that you can't order the complex numbers like we order the real numbers. Okay, let's do some applications. Applications to domains. Remember, we studied domains of functions throughout the first few lectures. Here's a more complicated function. How about f of x equals 64 minus x squared? What's the domain of this function? Well, the thing inside the radical has to be non-negative, and if you factor 64 minus x squared, you get 8 minus x times 8 plus x. And if you do a little interval analysis like we did before, you'll discover that any number between minus 8 and 8 satisfies that inequality, including the endpoints, and anything outside does not. So the answer is x less than or equal to 8, greater than or equal to minus 8. Here's a picture of that function. And it goes from minus 8 to 8, that's the domain, and down below I've indicated the domain on the number line. Do you recognize what that graph is? Right, that's a semicircle, and we'll talk about circles later on in this course. How about the domain of this function? 2 over x squared minus 4. That's a rational function, isn't it? What's its domain? Well, clearly x can't be 2 or minus 2. And hence you could write the domain as a triple union, minus infinity to minus 2, then you hop over minus 2 and go from minus 2 to 2, and then you hop over 2 and go from 2 to infinity. Kind of an interesting answer. All right, we're back to you being the teacher again. Here's a question I get all the time as a teacher, and I'll simplify it for you. Student comes to me and has scored 68 and 77 on the first 2 tests. And the student asked me, Professor Edwards, what do I need to get on the next test to bring my average up to an 80? Great question, very practical question. Student has a couple of test scores that aren't real high and wants to have an 80 average. What does the student have to score on the 3rd test? Well, you could construct this problem and solve it using inequalities. The scores of the first 3 tests will be 68 plus 77 plus the new score, the unknown score on the 3rd test. I'll call that score x. And the average of those 3 scores is 68 plus 77 plus x divided by 3. And I want that to be greater than or equal to 80. I want the average greater than or equal to 80. Let's solve this inequality. How do we do it? How about if we multiply by 3 first? And that would give us, on the right-hand side, 3 times 80, or 240. I can also add the 68 and the 77 and get 145. So the left-hand side is 145 plus x. And now move the 145 over to the other side, and we have x greater than or equal to 240 minus 145, or 95. So the student has to score 95 or better on the 3rd test to raise the average to 80 or higher. Again, I answer this kind of question all the time as a professor. Let's do a quick application. Remember we talked about the relationship between Celsius and Fahrenheit. The formula, or one of the formulas relating those 2 temperature gauges, is F equals 32 plus 9/5 C. F is the temperature in Fahrenheit, C is the temperature in Celsius, degrees Celsius. And suppose, again, we're back in Europe, and you're looking at your prescription drug, and it says you're supposed to store it between 40 and 70 degrees Fahrenheit. But your refrigerator in Europe, in your hotel room, is in degrees Celsius. What is the interval to store your prescription drug in degrees Celsius? Well, let's solve it. The Fahrenheit temperature has to be between 40 and 70, so I write 40 less than or equal to F less than or equal to 70, and then I solve this inequality. And one way to do it is first replace F with the formula for centigrade, 32 plus 9/5 C, and now keep solving, subtract 32 from the 3 terms, and then multiply by 5 and divide by 9, and you get C greater than or equal to 40 over 9 and less than or equal to 190 over 9. And if you punch that in on a calculator, you get 4.4, and I'm going to put a little horizontal line above the 4. That means the answer is really 4.44444444 forever. And on the other side, it's 190 over 9. If I put it in my calculator, I get 21.1 1 with a bar over it, which means 21.11111111 forever. Okay, great going. That was a tough lecture, I think. I think inequalities are harder than they look. And yet it's the language that we'll need to be comfortable with as we progress through this class. We've now sort of come to a break in the course. We've studied functions, and we've looked at polynomial functions, rational functions. We took a little detour to the complex numbers, and we came back and talked about inverse functions, and then today we talked about inequalities. Well, now we're going to begin in the next 5 lectures. We're going to begin studying a brand new class of functions. These are the exponential functions and their inverses, the logarithmic functions. So the idea of inverse function will come into play here. And we'll see lots of applications to carbon dating, compound interest, earthquake intensity, et cetera, et cetera. So I'm looking forward to these next few lectures because the logarithmic and exponential functions are very, very interesting. So I'll see you next time when we begin the exponential function. Thank you.